So last week we were talking about electrochemistry and describing various voltaic cells. We did a couple basic examples involving metals, and now I want to do a little bit more of a complex example. So here it says describe a voltaic cell based on the following. If we have the term voltaic cell, we know that that cell is spontaneous and that our cell potential has to be positive. So if we have two half reactions given by MnO4 minus in aqueous solution, giving us Mn2 plus in aqueous solution, our reduction potential for this half reaction is going to be positive 1.51 volts. If the second half reaction we were given is silver plus in aqueous solution, giving us silver solid, this half reaction has a reduction potential equal to 0.80 volts. And one of the things I also want to say about this particular reaction, we're given a voltaic cell based on these conditions, and this is going to be in acidic medium. Because we're given a couple half reactions here, but one thing you'll notice is that we have oxygen on the left of one of these half reactions, but it's not on the right. So how on earth do we get this equation balanced out? Because in order to balance out this total equation, we need to make sure that we account for all the oxygens in there. If we have a solution and it's in acidic medium, we know a couple things. One, it's an aqueous solution, so this is where we can get oxygen from the water. And that also means that there's going to be an excess of H plus ions in that solution compared to the OH minus ions. Okay? So here's our particular equation, or half reactions. We're given the cell potentials for each of these. We were told here that we have a voltaic cell. So this means this has to have a spontaneous reaction. So one of the keys that I said was look at the highest positive reduction potential, which in this case is going to be our permanganate solution. And this right here has to be the cathode. And at the cathode, reduction occurs. So what this means is that we can write our cathode reaction or our reduction half cell as MnO4 minus in aqueous solution, giving us Mn2 plus in aqueous solution. And we have to try to figure out how to balance this. Whenever we're balancing out half reactions, we have to balance out all the atoms that make up everything in the reaction, and we also have to balance out the charges. Okay? In this case, we have MnO4. So that means we need 4 waters over here on the right-hand side. If we add 4 waters to the right, we've added 8 hydrogens. So that means that we need 8 H plus over here on the left. So now we have to make sure in this overall process that our charges are balanced as well. On the left-hand side now we have an anion that has a -1 charge, and we have 8 cations with a +1 charge. So that means the overall charge on this side of the reaction is +7. And if we look over here on the right, we have a +2 charge for the manganese, a neutral water, so we have +2 over here on the right. In these redox reactions, electrons are being transferred, so we can add electrons to whichever side of the half reaction that we need to. You've probably heard the term oil rig used to try to give an abbreviation to these types of reactions. So that stands for oxidation is losing and reduction is gaining, and that's in terms of electrons. So if this is our reduction half cell, we would expect the electrons to be on the reactant side. In this case, we have a +7 charge for the reactants, a +2 for the products. So in order to balance out these charges, we need 5 electrons over here on the left-hand side. By adding 5 electrons here, that's 5 negative charges, so instead of +7, this is going to go down to +2, and we have an equal charge for the reactants and products. The cell potential for this half reaction is going to be positive 1.51 volts. Now we have to look at the reaction that occurs at the anode, or the oxidation half reaction. In this particular case, we're going to have silver solid being oxidized to silver plus. In this particular half reaction, we have to put an electron over here on the product side to balance out the charges. So now the reactant and product side is going to be neutral. This process we talked about last week, typically silver likes to be reduced down to silver solid. So this process is not favorable. And that's indicated by the half reaction potential of negative 0.80 volts for this silver reaction. So there are some cases in which we can make a reaction that does not want to proceed, go forward, and we would have to use something with a strong or a high positive cell potential for its reduction half reaction. So in order to add everything up here and get the overall reaction, we need to make sure our numbers of electrons cancel. In the first half reaction, we have 5 electrons. In the second, we only have 1. So we need to multiply everything in the second reaction by 5. Remember, we do not multiply the cell potential by 5. So the number of electrons will cancel out. And our overall reaction now is going to be MnO4 minus in aqueous solution plus 8H plus in aqueous solution plus 5 silver solids, giving us Mn2 plus in aqueous solution plus 4 waters as a pure liquid plus 5 silver plus ions in aqueous solution. And our overall standard cell potential for this reaction is going to equal positive 0.76 volts. So let me emphasize a few things in this particular reaction. If you look at the transition metals, we know that transition metals have varying oxidation states. Okay, we learned that back in the transition metal chapter. But the question is, when would a transition metal want to have a certain oxidation number? And what's a likely oxidation number for some of these cases? If we look at the periodic table and look at manganese, manganese is element number 25. So if we look at manganese as an atom, it has 5 d electrons and 2 s electrons. When we put it into an ion, manganese has 7 valence electrons. In the third row transition metals, manganese has the largest oxidation state, and that oxidation state is going to be +7. +7 is a really, really, really high oxidation number. So it's really tough to get manganese to go from +7 to +8, because now we're messing with a stable noble gas core. Okay? So if we look at this from a general perspective, do you think it would be easy for manganese to be oxidized? It's going to be very, very tough to oxidize manganese. So what manganese wants to do in pretty much every single case is it wants to be reduced. Notice that when we draw the reduction potential up for that reaction, it is a really, really large number. 1.5 is a very high reduction potential. And the reason for that is because manganese is already in a +7 oxidation state. It can't go any higher. It's not going to be able to be oxidized. So in every instance, manganese will have to be reduced. Okay? even though silver really wants to stay as silver solid and does not prefer to be oxidized, it will be in this case because we're putting it and coupling it with something else that really, can't be oxidized. Okay? And manganese can't be oxidized any further than +7. So these are some things to keep in mind when we're looking at particular redox reactions. Okay, what's the oxidation state of our transition metal? Does it like to be in a low oxidation state? How much farther can we oxidize that? Okay, so this is why in this case the permanganate ion, if we want something else to be oxidized, it's a great reagent to have because it's going to be reduced all the time. If something is reduced, something else has to be simultaneously oxidized. So we'll come back to that point in a second. But this gives the overall balanced chemical equation given two particular half reactions.